Hello everyone, welcome to your second tutorial session for ECE 457A. So in this session we are going to talk about some of the algorithms that you've learned and implement them in Python. Actually they're implemented before, so we're going to just review them and show you the codes, run the codes, and see the results. You can have access to codes using this link here in GitHub, and you can download the codes and run them, modify the codes, and whatever that you think is necessary to do to boost your learning. Alright, let's go through them. So I'm using VS Code for the codes. We have actually 6 files that I want to go through them one by one and explain that each file, the purpose of each file actually. So the first file is config.yaml. So the hyperparameters for your codes, functions, and algorithms are defined here, and you can modify them. For example, if you want to use local search, you can copy and paste it here, or if you want to use iterative local search, simulated annealing as well. And you can choose your cost function. We have like 8 different cost functions here that you can use. You can add more if you want. For the algorithms as well, you can add more if you want. Then you need to specify the dimension of the your cost function, the variables in your cost functions. We mostly work with 2-dimensional cost functions, but you can add more. And for each algorithms defined in this .py file, search algorithms, you can specify the hyperparameters as you want. So the first one is the config.yaml. You can use JSON as well instead of YAML, but the difference is that when using YAML, you can write comments, but in JSON you can't. So we prefer YAML over JSON. The next file is the init.py. So it's empty, but the purpose of this file is to let the Python interpreter know that this directory, that this init.py is inside of it, contains like codes for Python module. So in other words, this directory is a Python package. So this directory is utils. As you can see here, in utils we have init, cost functions, plot utils, search algorithms. So by using the init.py, we're specifying that this utils is a package that we want to import some .py from it and use it in our main code. The next one is the cost functions. Here we have implemented for you 8 cost functions. The first 4 are from this paper. Sorry, this one. Yes, tree-based optimization and algorithm for metaheuristic optimization. So these are the cost functions, the first 4 cost functions implemented in the Python code. This is the plot for the cost functions and the functions, formula for the functions as well, and the range as well are specified here. And for the next four, func 7, 8, 9, and 11, you can find here 7, 8, 9, and 11, and also the formula for that, and bounds and range as well. So these are all some benchmarks, some benchmark like optimization cost functions that you can use. You can add more from these papers if you want. Then we have plot utils that mainly plots your results, your cost functions in 3D and 2D. Then we have search algorithms here. I've implemented for you 3 of your algorithms: local search, iterative local search, and simulated annealing. That you can basically choose whichever you want to use. After that, you have your main file that runs the algorithms and does the optimization using the selected method of your choice. So one of the purposes of these codes is that to show you how modular programming is. In other words, separating the functionality of your program into independent and interchangeable modules. So you're subdividing your program into other subprograms. It's one of the best ways to show that you're skilled in programming and to keep your code clean and neat. Okay, for the main file, we have YAML. We need to import YAML. We need to import like dict if you're using a dictionary from typing, and from utils that we talked about, which is a package, a folder that we define here. And in this folder, there are 4 files: init, cost function, plot utils, and search algorithms. We're importing them here to use them. We've defined our first function, the main function. So using config, first we specify the cost function. So what is our cost function? You need to specify your cost function in the config. So for example, if the cost function here is func11, for example, or let's use the first one, sphere, save it. So in your main, this part of code will run because your cost function is now sphere. And from cost functions, sphere is chosen. So your cost function is now a sphere. And the range for that cost function is from -100 to 100 for each dimension. For example, if you're specifying your cost function to have like 3 dimensions here, in the main we will have like a list that contains 3 lists inside of it, and each list specifies the range for each dimension. But for the plot reasons, we're using 2, so we can plot them in 3D and 2D. So this one specifies the range, and the rest of the code does the same for different cost functions. For example, if I change my cost function here to func7, save it, main, and this part of the code will run because now the cost function is 7. Then we move on to the algorithm. So we need to choose our algorithm. Then again, in config, For example, we're using local search algorithm. So we type local search here, and because this part of code is true, this part of code will run, which basically runs the search algorithm, the local search from the search algorithm, and gives you the best result, the best solution, and the history of convergence using this one. So basically that part of the code runs this algorithm. And if your dimension is 2, as you specified here, this part of the code will plot the results for you. And this part mainly runs the whole code. So first opens the config.yaml and reads it. And after that, it'll just run the main config. This part for the code. Okay, one more thing that I want to talk about here before showing you the plots is that first we're using typing in our codes. It's not necessary, but we want to use it to add use it to add the types of variables or parameters or functions. For example, here we're importing a list because we're using a list here. It specifies the type of this parameter inside this function. So it's a list of float values. And this function, each of these functions actually will output a float value. It's not necessary to write this part, but for the sake of being complete, we can write it. We also have this in our search algorithms. For example, cost function is a callable, which is a function defined in the cost functions. Maximum number of iterations is an integer. Convergence threshold is a float. So using this, we're just specifying the type of the parameters that are feeding into these algorithms. And this is the output of the function, of local search function, which is a tuple. All right, we are using TQDM, which comes from the Arabic word for taqaddum, which means progress, in order to show you the progress bars in the for loops of the algorithms. For example, you have a while loop here, and using this progress bar using TQDM, we will show the progress bar of maximum number of iterations that you're allowed. And we also have history, the history of the values that the algorithms found. Well, here it's mainly because we want to show the trajectory of convergence in the plots. So just for the sake of showing you how the algorithms converged. Or the history is also necessary for taboo search, which is another optimization algorithm that you'll learn in the future. Other than that, you don't need to use them because they increase the space complexity, and you don't want to do that. Okay, so I think that was all about the different parts of the codes. We can dive deeper into the algorithms, for example, local search. For local search here, you have two hyperparameters, convergence threshold and maximum number of iterations. So let's set the maximum number of iterations to 1000 and the threshold to 0.01, dimension 2. Let's use the sphere function as our cost function and local search as our search algorithm. Now let's run the code. Okay, so this is the 3D plot for the cost function, and the optimization path is shown with red dots or red circles, and the best solution, best result, is the blue one. So this path actually shows the trajectory of convergence in 3 dimensions for x2, x1, and x2, and this is the cost function. You can have a 2D plot for that, x1, x2. It's actually a heat map showing you the value of cost with different colors and the trajectory of convergence. As you can see, this is how the algorithm approached the best result, which is not the best result here, but this is what the algorithm found. We can use a different function, for example, function 7. So in our config, we can use this function, 2 dimensions, and let's go for maybe 2000 iterations, save, main. Okay, so I think we found the first one as the best solution, maybe. No iterations. Let's change it to, I don't know, let's go with 100 and local search, function 11. Okay, this is the 3D plot of function 11. Red dots show the optimization path, and the blue one is the best solution. This is also the 2D plot for that. So you can use different algorithms, add different algorithms to this code, and different cost functions. For that, for example, if we are going to go through this code line by line, so the first step is to set the initial value for x. So if it's none, we'll get some random values from the uniform distribution in the range in which the bounds of the function are specified for each dimension. After that, we say that the current x is the initial value and the current cost is specified using the cost function, which is here. you can see in the main part of the algorithm, here for local search, we're given it the cost function that is specified here. Then we save the history in a list. This line of code is to show you the progress bar. Convergence is set to false, number of iterations 0, while not converged. So let's check the algorithm. For example, local search. While not converged, do this. Generate neighborhood. Okay. So we use a Gaussian distribution with the current x as the mean value and 0.1 as the standard deviation. You can choose other values of your choice to generate a distribution over your current value in order to just draw a sample from it and introduce it as your neighboring solution or your neighboring candidate. After that, we need to check to see if that chosen value is in the specified range. For example, remember for the sphere, we specified -100 to 100 for both dimensions. So we need to check if this chosen value is in the range, and if it's not, we will clip it using this function. After that, we find the cost of the neighbor, and if the cost of the neighbor is less than the cost of the current value, we set the current value as the neighbor, current cost as the cost of the neighbor, and if the cost of the current is less than the convergence threshold, or we actually exceeded the maximum amount of iterations, we set the convergence to true and come out of this loop, this while loop, and just introduce the best value and the best cost for this algorithm. So here, because we have the history, we can use the best, like the argmin for that, and choose the minimum value of in the trajectory. So we're allowed to do that, but basically we should not save the history as it increases the space complexity. So every step is basically based on this one. So we evaluated the fitness of the function. If better fitness, then update the solution. Here. If better fitness, update the solution. And this is a condition in order to break out of the loop. This also updates the progress bar by units of 1. And the next algorithm is the iterative local search. So in this algorithm, it first calls the local search, and the difference here. So first the algorithm calls the local search, produces the value, appends the solution, and samples from the optimization landscape. So this sampling from the optimization landscape happens here. So we have a uniform distribution over the range in which the dimensions are specified. and we sample some solution and set it to current. So in this way, we're sampling from the optimization landscape after calling the local search this function. And this one is for simulated annealing. The temperature is set here. For the temperature, you have a float value. So temperature is a float value, which is specified in the config. For example, 3, alpha and beta you have. The value, you need to specify the values here. And the temperature decrement method, we have 3 options for that: linear, geometric, or slow. So they're specified here. For example, if you choose linear, this line of code will run. If you choose geometric, this line of code will run. And if you choose slow, this line of code will run, all based on the formulas in your lecture notes for simulated annealing. So this is the decrement the temperature T part. This. And value is chosen. The method is actually chosen based on one of this. Here we'll calculating delta E, cost of neighbor minus cost of the current solution. This one. Evaluate fitness function and calculate delta E. And if delta E is less than or equal to 0, then update the solution. Else, sample from the uniform distribution and see if this sample is less than or equal to this value, then update the solution. So if delta E is less than or equal to 0, we're updating the solution, appending that solution to the history, or else we're using a uniform distribution, sampling from a uniform distribution between 0 and 1, and see if this sample is less than or equal to this value, then update the solution. And decrement the temperature, show the progress bar, and get the best result. Then again, because we are having the history of the cost and x, we can use argmin and find the index for the best result. Let's run simulated annealing, linear, alpha. Using the linear one, we have alpha 0.1, temperature 3, maximum number of iterations 50. So in the main file, in the config file, I need to change this to simulated annealing. I want to apply it on function number 9. Save it. Main, and let's run it. So because we were using function number 9, the cost function is function number 9. The range is between -5 and 5 for both dimensions. We have specified the number of dimensions as 2. And search algorithm is simulated annealing. Simulated annealing gets the maximum number of iterations as 50, and temperature, alpha, beta, range, initial value, and temperature decrement method. Okay, this is the 2D plot. You can see the trajectory of convergence. Now let's apply iterative local search on, for example, this function. So we have two loops here because in the outer loop, we have the inner loop, which is the loop for the local search. So maximum number of iterations for LS, local search, 100, and maximum number of iterations for the outer loop, which is the main loop for example, here in iterative local search, we have this outer loop and we have this inner loop inside of local search. So we specify the number of iterations for the outer loop is 10 and for the inner loop 100. And the convergence for threshold, let's decrease it. Save, main, run. And this is the progress bar that we talked about using TQDM. This is how the trajectory actually moved to find the best solution. And this is the 2D plot for that. Okay, I think that's it for now, and this concludes the tutorial, the second tutorial of for this course. And see you next time.